So as you probably noticed, we are going through the science part of it, the human action part of it, and the human attempts to slow down or adapt to climate change and so on, and the science of detecting change, attributing change, and so on. Let's get back to some of the fundamentals that we already learned, but let's reinforce some of the concepts. Global warming obviously has everything to do with the greenhouse effect of the Earth. And this is a good thing, right? Because as we said, the greenhouse effect on Venus and Mars have been runaway positive feedbacks, getting very hot on Venus, very cold on Mars, whereas we have what is called sometimes the perfect blanket or the Goldilocks syndrome. I don't know if you know the Goldilocks story, a blanket that's not too cold, not too hot, just perfect, right? So our greenhouse blanket is just perfect. But what perfect for what? Generally, we think about life. We know life is here on Earth in all its glory, but we constantly keep looking for life elsewhere. And as I mentioned in another podcast, some chemicals detected on Venus seem to indicate that there is some biotic activity, because the probes can sense non-equilibrium atmosphere and look for chemicals that do not come from abiotic sources, inorganic reactions. They can only come from biotic activity, something like phosphine. Okay, so greenhouse effect is very important. In a simple sense, it's explained usually this way. Comes from the greenhouse that we all know of, where it's a transparent structure which allows sunlight to come in and traps the outgoing long wave radiation, right? Not a perfect analogy, but nonetheless it works. So it takes the incoming sunlight that is allowed to come in, heats whatever is inside, and the heat is trapped, and obviously these can be very productive biomes for growing vegetables and various flowers and so on, right? So that's our greenhouse effect. And incoming energy is in short wavelengths, as we saw. Everything gets heated, and energy is going back in the long wave. And this is being trapped by the so-called greenhouse gases. To look at the spectrum, we have already mentioned this many times. Here is the energy on this axis. Here is the sun's radiomagnetic spectrum, which goes all the way to gamma rays, X-rays, down into the energetic blue UV that gets trapped in the stratosphere by the ozone, and then the visible. So most of the energy that is entering the Earth's atmosphere is in the visible. And the energy that is then used to heat up everything is going out in the long wave. So you can see the clear shift in the wavelength. On the horizontal axis you have wavelengths in micrometers, and you can see that visible is centered on half a micrometer, whereas the outgoing long wave is centered around 10 micrometers. So obviously there is a huge shift in the spectrum of energy that is going out. So what is greenhouse then? Essentially, that means there are certain molecules that are air that comprise the atmosphere. We have N2 and O2 comprising most of it, 79 and 20, or 71 and 20. And then you have argon, and then you have all these other trace gases. Remember, CO2 is only 0.04%, and yet it's powerful because it allows shortwave to go in, but traps the outgoing long wave. We'll look at the molecular structure and see how that happens. To revisit briefly our radiation budget, then we had 100 units coming in, just to make things simpler. 23 was being absorbed in the dust, 19 of it by water vapor, ozone, various other absorbing aerosols. We haven't defined aerosols, but I think we did. Anything that's floating around in the atmosphere that can be transported, lifted from the surface or from the trees or whatever, is called an aerosol. Could be sea salt, could be bacteria, could be dust, could be black soot, and so on and so forth. And clouds absorb about 4%, so 23 units is lost, absorbed in the atmosphere. And obviously Earth's albedo is on average 0.3, so 30 of the 100 units are reflected back as shortwave, which is just backscattering by the molecules in the atmosphere, reflected by clouds. So clouds absorb a small amount and they reflect a significant amount. Right? Why is it important? Because when we look at energy balance, we have to see, as we keep increasing greenhouse gases, as we said before, are clouds a positive feedback or are they a negative feedback? As warming increases, water vapor increases, will clouds increase and reflect more energy to compensate for the greenhouse effect of the greenhouse gases, or will it be less effective and allow trapping of more energy? This is always critical. And from the surface there is about 6 units being reflected. Obviously when the angle of incidence is high on the ocean is dark, forests are dark, deserts are lighter, high albedo, snow and ice have high albedo, and so on and so forth. So what do we have? We have 30 units reflected as shortwave, 23 units absorbed in the atmosphere, and remaining 47 is going to hit the surface. So less than 50% is actually hitting the energy. But greenhouse gas is like a blanket. Imagine yourself under a blanket. When you feel cold, you put on a blanket because it traps the body heat and creates temperatures that are warmer. That's what the greenhouse blanket is doing. So long wave radiation from the surface, 10 can go directly, whereas emission by H2O, CO2 and O3 together with the... So this is long wave, which means what? When we say H2O, CO2 and ozone are sending out, emitting long wave, they are absorbing the energy coming from the surface, they're getting warmer, and they are sending out the energy. Remember our black body radiation calculations. Sigma temperature to the fourth, sigma T to the fourth. Any warming is going to be quadratically increased in terms of radiation. So that's a built-in negative feedback, right? If temperature increases, greenhouse gases get warm and they emit more radiation. So that's negative feedback. Unfortunately, they also send the energy back to the surface. And remember what we said, the most important thing about greenhouse effect is that the surface gets warmer, because it not only receives this short wave, but it also receives the long wave, because the long wave is going in both directions. It's going out to space as well as back to the surface. Okay, that's why you get numbers that are bigger than 47 units. For example, it bounces around. So conduction is very small in the atmosphere, as we talked about. Molecular conduction density is low even in the ocean. It's the advection in the atmosphere. It's the convection that can move the heat, not conduction. Very small. Okay. Evaporation, breaking of the hydrogen bonds, lifting the energy, putting in the atmosphere, clouds reflecting. So we have to match 100 minus 30. That's the net coming in. So outgoing has to be 10 plus 40 plus 20, that's 70. This is the equilibrium. What's happening under global warming? We are basically reducing the amount going out. This is in a crude sense. We are trapping more energy. But it's not that simple, because the atmosphere is just going to emit at a different temperature. It's complicated, but just think of it in this simple way, that greenhouse gases are reducing the amount of energy being lost to space, and that's how we get the greenhouse effects. I will do this in the next podcast again, because that's a important little diagram. We will see what are the spectral distribution of the greenhouse effects of different greenhouse gases. Okay, I'll also come back to the structure of the molecules to reinforce the concepts, but let's look at this in the next podcast.